We're looking at Neptune's orbit and it's not following Newton's laws. This is odd. For ages, Neptune has captivated scientists and dreamers with its mysterious charm hidden behind a veil of secrecy and passion. But, because of tireless efforts in scientific discovery, scientists are on the verge of a remarkable breakthrough. The clearest pictures ever taken of this faraway icy giant. These images provide a peek into Neptune's stormy atmosphere, revealing a surprising finding that will change how people see the outer edges of the solar system forever. What lies beneath Neptune's veil of clouds? What secrets do its icy depths conceal? Join us as we unravel the shocking discovery of the closest images of Neptune ever taken. In August of 1977, Voyager 2 embarked on an extraordinary journey through our solar system, venturing where no spacecraft had gone before. It set out to explore the outer reaches of our celestial neighborhood, marking a remarkable moment in space exploration. After a 12-year journey, Voyager 2 reached Neptune in 1989. As it approached the distant ice giant, it captured breathtaking footage that unveiled a majestic world shrouded in stirring bands of azure clouds. Imagine witnessing this distant sibling of Jupiter adorned in shades of mesmerizing blue. Among Neptune's mysterious features, Voyager 2 detected a colossal storm raging across its atmosphere, resembling a massive slate-colored uproar. Additionally, the spacecraft discovered 4 mysterious rings encircling the planet, along with 6 previously unknown moons, adding to the allure of this distant realm. Despite its epic voyage spanning 4.3 billion kilometers, Voyager 2's encounter with Neptune was fleeting, lasting only a few hours. However, this brief rendezvous provided humanity with unprecedented views of the distant ice giant, capturing the essence of Neptune's captivating beauty. When considering Neptune, many of us recall the iconic image memorialized by Voyager 2, a portrait showcasing the planet's towering white clouds and turbulent storms, all bathed in a famous yet mistaken hue of blue. In reality, Neptune's true color is a softer, lighter shade of greenish blue, a subtle detail often overlooked in the grandeur of space exploration. When venturing online in search of more snapshots of Neptune, people quickly notice a scarcity of images. Despite Voyager 2's impressive feat of flying within a hair's breadth of just 4,950 kilometers from Neptune's surface, the number of available photos remains surprisingly low. What makes Neptune so elusive to capture on camera? Imagine Neptune resides a staggering 30 times farther from the Sun than we do on Earth. This vast distance means it receives only a fraction of the sunlight that our planet enjoys. Consequently, when Voyager 2 finally caught up with Neptune after its gravity-assisted journey past other outer planets, it was hurtling through space at an astonishing speed of 27 kilometers per second. While Neptune may seem like a distant speck in the universe, its allure lies in its perplexing blue hue and mysterious atmosphere. But capturing these mesmerizing details proved to be quite the challenge for Voyager 2. With Neptune receiving only a mere 0.1% of the sunlight that reaches Earth, the spacecraft struggled to snap clear, non-blurry photos amidst the dimly lit expanse. Voyager 2's ingenuity knew no bounds. By deftly working its thrusters to swing past and employing extended exposure techniques, the spacecraft managed to capture and transmit back to Earth some of the closest and most mesmerizing images ever taken of Neptune. Just a couple of hours before Voyager 2 zoomed past Neptune, it captured an incredibly detailed picture. In it, scientists got a close-up view of some interesting features high up in the planet's atmosphere, long, wispy clouds that resemble the cirrus clouds we see on Earth. They're not made of water vapor like Earth's clouds. These clouds are crafted from frozen methane, giving them a surreal appearance. Imagine these cloud formations stretching for thousands of kilometers, running parallel to Neptune's equator. They're not just some puny clouds either. Each streak measures between 50 to 200 kilometers wide. These clouds are so high up that they cast shadows on the hazy layer about 50 kilometers below. What's even more mind-blowing is that even though Voyager 2 had already checked out all the other gas giants before Neptune, it wasn't until Neptune that people got their first ever glimpse of these elusive cloud shadows. As evidenced by the grainy image captured, these high-altitude clouds are like fleeting guests in Neptune's atmosphere, always on the move and changing shape. Recent observations from the Hubble Space Telescope revealed that these clouds can form and disappear in the blink of an eye, showcasing the dynamic nature of Neptune's weather patterns. When this picture was captured, strong winds would have been swirling around the ice giant, some blowing as fast as 2,100 kilometers per hour. That's 3 times quicker than winds on Jupiter and almost 9 times speedier than those on Earth. Voyager 2 revealed that Neptune experiences some of the most extreme weather in the solar system. When the spacecraft flew by, it encountered a striking example of this: the Great Dark Spot, a large oval-shaped cyclone resembling Jupiter's Great Red Spot. This immense weather system was roughly the size of the entire Earth. What's fascinating about this image is that the center of the storm appears to be relatively clear of clouds, forming a vast dark void slicing through Neptune's atmosphere. Neptune is an incredible ice giant, about 4 times wider than Earth. Its radius is around 15,300 miles, and it has an enormous volume of 15 trillion cubic miles. To put that in perspective, Neptune is 58 times larger in volume than Earth. This fascinating planet is mostly made of water, methane, and ammonia. Unlike Earth, Neptune doesn't have a solid surface. Instead, its thick atmosphere extends deep into the planet, reaching down to a mantle made of methane and ammonia ice surrounding a rocky core. Interestingly, scientists think that Neptune might even have a superhot ocean hidden deep inside. Despite its icy name and outer appearance, the conditions inside Neptune are anything but cold. But how can a planet sustain such an ocean when it is so far from the Sun? Sunlight takes a whopping 4 hours to reach Neptune's massive surface. Neptune is incredibly cold, with an average atmospheric temperature of -360 degrees Fahrenheit, making it one of the chilliest places in the solar system. Interestingly, most of Neptune cooled down between 2003 and 2018, though there was some warming near the South Pole from 2018 to 2020, likely due to seasonal changes in the atmosphere's chemistry. The mystery of how an ocean might form inside this icy giant remains unsolved. However, scientists have some theories. One idea is that internal heating caused by gravitational compression or interactions between Neptune and its largest moon, Triton, might play a role. Yet not all researchers agree. For instance, scientists Sloan, Viktorovich, and Insall argue that the chances of oceans forming on Neptune due to its internal heat are quite slim, estimating it at only 15% right now. Their calculations suggest that it might take 1 billion years for the probability of such an ocean to rise to 40%. Assuming the giant continues to cool down over time. One interesting theory for Neptune's immense internal energy is that it might have collided with a cosmic object long ago. Neptune stands out as the only planet that radiates nearly 3 times more energy than it absorbs from the Sun. This unusual energy output might be linked to the planet's significant 28 degrees tilt on its axis, which is quite similar to Earth's tilt. This tilt means Neptune experiences seasons much like Earth does, but with a twist. Each season on Neptune lasts around 40 years. To put it in perspective, 1 Neptune year equals 165 Earth years, but a day on Neptune is just 16 hours long. This fast rotation generates extremely strong winds. Neptune's atmosphere is composed mostly of hydrogen, making up 80%, with helium accounting for 19% and a small fraction, about 1%, of other gases including methane. The striking blue color of Neptune is a result of methane clouds in the upper atmosphere, which absorb red light and reflect blue. Methane plays a significant role in shaping the atmospheres of both Neptune and Uranus. Despite being the farthest planets from the Sun in our solar system, these ice giants still receive a significant amount of solar radiation, albeit much less intense than what inner planets like Earth receive. Neptune's vivid blue coloration has captivated astronomers for centuries, but the exact mechanisms behind its striking color continue to interest scientists. One fascinating aspect is the presence of high-altitude clouds composed primarily of methane ice crystals. These clouds scatter sunlight in a way that enhances the blue coloration, similar to how Earth's atmosphere scatters sunlight to create blue skies. Furthermore, Neptune's dynamic atmosphere exhibits a multitude of features, including massive storms and powerful winds. On the other hand, Uranus presents a different aesthetic with its muted pale blue color. This planet's unique tilt, where its axis is nearly parallel to its orbital plane, results in extreme seasonal variations. During its long polar winters, Uranus experiences prolonged periods of darkness, hindering the formation of high-altitude methane clouds that contribute to its overall coloration. In addition to methane, both planets' atmospheres contain trace amounts of other gases, including hydrogen, helium, and ammonia. These gases, along with the intricate interplay of temperature, pressure, and atmospheric dynamics, create a complex and dynamic environment worthy of scientific exploration. Neptune holds many mysteries within its icy depths. Its intense blue coloration, derived from methane in its atmosphere, adds to its allure. But beyond its captivating hue lies a world of extremes. The storms that rage across Neptune's surface are not just any storms. They are colossal tempests, some spanning thousands of kilometers. These atmospheric disturbances, marked by dark and white patches, are the result of Neptune's rapid rotation, completing a day in just 16 hours. This rapid rotation generates incredibly strong winds that whip around the planet, reaching speeds of up to 1,500 miles per hour, faster than the speed of sound on Earth. The turbulent weather patterns observed on Neptune are among the most dynamic in our solar system, showcasing the planet's complex and ever-changing atmosphere. Neptune's dynamic weather patterns are not just a spectacle to behold. They also provide valuable insights into planetary science. By studying these storms and atmospheric dynamics, scientists gain a deeper understanding of how planetary weather systems operate under extreme conditions. This knowledge extends beyond Neptune to other gas giants and even exoplanets, offering a comparative perspective on the diverse range of planetary atmospheres found throughout the cosmos. Neptune's dynamic atmosphere continues to intrigue and inspire scientists and stargazers alike. As our understanding of this distant ice giant grows, so too does our appreciation for the complexities and wonders of our solar system. With each new discovery and observation, Neptune reveals more of its mysteries, inviting us to delve deeper into the realm of planetary exploration. Neptune's enigmatic allure extends beyond its captivating blue hue and tumultuous storms. Among its most intriguing features are its rings, which add a delicate yet mysterious dimension to this distant ice giant. Discovered during Voyager 2's historic flyby in 1989, Neptune's rings are faint and dusty compared to the prominent rings of Saturn. Composed of dark, microscopic particles, these rings orbit Neptune in a complex interplay of gravitational forces. Unlike Saturn's well-defined rings, Neptune's rings are faint and challenging to observe from Earth. They consist primarily of three main arcs named after astronomers who played pivotal roles in their discovery: Gall, Leverrier, and Adams. These arcs are believed to be maintained by the gravitational influence of nearby moons, which shepherd the ring particles and prevent them from dispersing into space. One of the most puzzling aspects of Neptune's rings is their dynamic nature. Unlike the stable rings of Saturn, Neptune's rings exhibit variability in brightness and structure over time. This variability suggests ongoing interactions between ring particles and external forces, such as micrometeoroid impacts or gravitational disturbances from passing moons. Neptune's largest moon, Triton, is a world unto itself, with a surface carved by icy volcanoes and geysers spewing nitrogen gas into space. Discovered just weeks after Neptune itself in 1846, Triton orbits the planet in a retrograde motion, opposite to Neptune's rotation. This unusual orbit suggests that Triton may have been captured by Neptune's gravity after forming elsewhere in the solar system. Triton's icy surface is a testament to the extreme cold of its environment, with temperatures plummeting to -391 degrees Fahrenheit, -235 degrees Celsius. Despite these frigid conditions, Triton exhibits a dynamic geological landscape marked by cryovolcanism, a process where icy volcanoes erupt nitrogen, water, and other volatile materials instead of molten rock. The discovery of cryovolcanism on Triton was a revelation in planetary science, challenging previous assumptions about the geological activity of icy worlds. These cryovolcanoes, along with dark streaks and icy plains reminiscent of Earth's polar regions, paint a picture of a dynamic and evolving moon shaped by the interplay of internal heat and external forces. Triton's unique characteristics have sparked scientific interest in exploring its surface in greater detail. A proposed mission, Trident, aims to send a spacecraft to Triton to study its atmosphere, surface composition, and geological activity up close. Such a mission could provide valuable insights into the evolution of icy moons and their potential for harboring life-sustaining environments beyond Earth. Beyond Triton, Neptune's system of moons includes a diverse array of smaller satellites orbiting at varying distances from the planet. These moons, ranging in size from tiny irregular rocks to substantial objects like Triton, offer clues to the formation and evolution of Neptune's satellite system. Some moons, like Nereid, exhibit highly eccentric orbits that hint at past interactions with other moons or external gravitational influences. Neptune's moons also play a role in shaping the planet's magnetosphere, a region of space around Neptune influenced by its magnetic field. Unlike Earth's magnetosphere, which is generated by the planet's iron-nickel core, Neptune's magnetosphere is primarily generated by the interaction between its rapidly rotating atmosphere and the solar wind, a stream of charged particles emanating from the Sun. Studying Neptune's magnetosphere provides insights into the planet's internal structure, atmospheric dynamics, and interactions with the solar environment. These studies help scientists understand the broader implications of magnetic fields in planetary science, from their role in protecting planets from solar radiation to their influence on atmospheric escape processes. In addition to its scientific significance, Neptune continues to captivate imaginations with its mysterious allure and distant beauty. From its dynamic atmosphere and tumultuous storms to its intricate ring system and diverse moons, Neptune offers a window into the complex and evolving nature of our solar system's outer reaches. As exploration technologies advance and new missions are proposed, Neptune and its moons remain targets of scientific inquiry and wonder. Each discovery adds to our understanding of planetary formation, evolution, and the potential for life beyond Earth. Neptune's distant realm invites us to explore, question, and appreciate the vastness and diversity of our cosmic neighborhood.